Every single time you open Google Maps, every time your phone locks onto your location in seconds, every time a military pilot drops a precision munition on a target from kilometers away, without ever seeing it with their own eyes, all of that is happening because of a constellation of satellites quietly orbiting Earth thousands of kilometers above your head. That network is GPS. And on April 21st, 2026, the United States took one of the most significant steps in the entire history of that system. SpaceX launched the final satellite in the GPS-3 block, a moment that U.S. Space Force, Lockheed Martin, and every engineer who has worked on this program for the past decade had been building toward for years. Accomplished is not just a headline, it is the literal truth, and the full story of what happened, and what it means for every human being on the planet who has ever looked at a map on their phone is worth understanding properly. The launch happened in the dead of night. A SpaceX Falcon 9 rocket lit up the sky above Cape Canaveral Space Force Station in Florida at exactly 2:53 in the morning Eastern Time on April 21st. The rocket lifted off from Space Launch Complex 40, carrying a Single Vehicle 10, or SV-10, into the darkness above the Atlantic Ocean. The satellite had been delayed by 1 day due to poor weather conditions in the booster recovery zone, but once the weather cleared, the Falcon 9 performed exactly as expected. Everything about this launch was crisp, professional, and executed with the kind of precision that SpaceX has made look routine, but that represents thousands of hours of engineering work behind every single flight. The booster used for this mission was Falcon 9 First Stage B-1095, flying for its 7th time. It had previously launched 6 batches of SpaceX's Starlink internet satellites, and now it was being trusted with one of the most strategically important payloads in the entire United States national security space architecture. About 8.5 minutes after liftoff, B-1095 separated from the upper stage and began its controlled descent back toward the Atlantic Ocean. It touched down on the SpaceX Droneship named Just Read the Instructions, and that touchdown carried a significance that went beyond just another successful landing. This was the 158th and final Falcon 9 landing that Just Read the Instructions will ever support. SpaceX announced during the launch commentary that the Droneship will now be retired from Falcon 9 operations and dedicated entirely to supporting the Starship program going forward, a historic vessel for a historic mission. Meanwhile, the upper stage continued powering its way through the darkness toward medium Earth orbit, the region of space, thousands of kilometers above the surface where the GPS constellation operates. Approximately 90 minutes after liftoff, SV-10 was deployed from the rocket's 2nd stage. Signal acquisition was confirmed shortly after. The satellite was alive in orbit, talking to controllers on the ground. And with that confirmation, a program that has spanned years of engineering, production, testing, and launch operations reached its conclusion. GPS-3 SV-10 was in space. The final piece of the GPS-3 block was in place. Now let's talk about what this satellite actually is and why it matters so much, because the technical story here is genuinely extraordinary. The GPS-3 program is a complete generational upgrade of the American GPS system, a modernization effort designed to replace aging satellites that were built with decades-old technology and to bring the entire navigation constellation into the 21st century. The GPS-3 satellites, built by Lockheed Martin at their facility in Waterton, Colorado, deliver 3 times greater positional accuracy than the legacy satellites they replace. They carry 8 times stronger anti-jamming capability. In a world where adversary nations have been actively developing technologies designed to interfere with GPS signals, jamming systems, spoofing systems, directed energy systems, that 8-fold improvement in anti-jamming is not just a technical upgrade. It is a national security necessity. The GPS constellation is used by the U.S. military for literally everything: navigation, targeting, timing, communications, synchronization, drone operations, precision strike, and a GPS signal that can be jammed is a vulnerability that enemies can exploit. The GPS-3 block closes that vulnerability in a way the previous generation simply could not. For military users specifically, the GPS-3 satellites provide what is known as M-code signals, encrypted high-powered navigation signals, reserved exclusively for military use, that are significantly harder to jam or spoof than the civilian signals that broadcast alongside them. M-code was designed for operations in contested environments, the exact environments that modern military planners are most concerned about, where sophisticated adversaries will attempt electronic warfare against U.S. forces from the opening moments of any conflict. With SV-10 now in orbit, the U.S. Space Force has completed the GPS-3 constellation that gives warfighters around the world access to the most resilient, most accurate, and most jam-resistant military navigation signals ever deployed. But this is not just a military story. 6 billion civilian users around the world depend on GPS every single day, and the GPS-3 upgrade matters enormously for them too. The improved accuracy delivered by the GPS-3 block means better performance in urban environments, in cities where tall buildings reflect and scatter GPS signals, making positioning less reliable. The GPS-3rd satellites also broadcast additional civilian signals that improve international compatibility, meaning GPS works better alongside other global navigation systems, like Europe's Galileo, Russia's GLONASS, and China's Beidou. For the billions of people who use location services daily across every industry, from agriculture to aviation to shipping to emergency services, the completion of the GPS-3 constellation is a direct improvement to the quality and reliability of a service they depend on, but rarely think about. The satellite itself carries a name that connects this mission to a remarkable story from history. SV-10 was given the nickname Hedy Lamarr, named after the Austrian-American actress and inventor who, in the 1940s, co-developed a frequency-hopping spread-spectrum communication system originally designed to make torpedo guidance signals harder for the enemy to detect and jam. That patent, filed in 1942, laid the theoretical groundwork for technologies that would eventually become GPS, Wi-Fi, Bluetooth. Hedy Lamarr spent much of her life without recognition for this invention, but the technology she helped create now underpins the global digital infrastructure that billions of people use every hour of every day. Naming the final GPS-3 satellite after her is a recognition that is long overdue. Every previous GPS-3 satellite was named after a trailblazer, and the 10th and final one carries perhaps the most fitting name of all. SV-10 also carries 2 technology demonstration payloads that make it particularly interesting beyond just completing the GPS-3 block. The first is an optical cross-link demonstration system, a laser communications technology that allows GPS satellites to communicate directly with each other in space rather than relying on ground stations to relay signals between satellites. This is a capability that will become standard on the next generation of GPS satellites, and SV-10 is testing it in real orbital conditions for the first time. Satellites that can talk to each other directly in orbit are significantly more resilient. The constellation continues operating at full capability, even if ground infrastructure is disrupted or destroyed. In a serious military conflict, that kind of orbital resilience could be the difference between a GPS constellation that keeps functioning and one that goes dark under attack. The second demonstration payload is an advanced digital atomic clock, a digital rubidium atomic frequency standard, or DRAFS. Atomic clocks are the heart of GPS. The entire system works by measuring tiny differences in the time it takes signals from different satellites to reach a receiver. The more precise the clocks, the more precise the positioning. The DRAFS clock on board SV-10 represents the next step in timekeeping accuracy for GPS satellites, and the data gathered from its performance in orbit will directly inform the clock designs going into the next generation program. 2 demonstrations riding alongside the primary mission, and both of them directly building the technology foundation for what comes next. What comes next is called GPS-3F, the follow-on generation that Lockheed Martin is already in production on. If GPS-3 was a major leap forward from the legacy constellation, GPS-3F is going to be another leap beyond that. The IIF satellites will deliver 60 times greater anti-jamming capability compared to the original GPS legacy satellites. They will carry regional military protection capability, a system that can dramatically increase signal power over specific geographic areas during a conflict, essentially creating a navigation umbrella over a theater of operations that becomes almost impossible to jam. They will also include a search and rescue payload, making them part of the international COSPAS SARSAT system that helps locate people in distress anywhere on Earth. And they will carry a laser retroreflector array that allows ground stations to precisely measure satellite positions using laser ranging, improving the accuracy of the entire constellation. The GPS-3 block that just completed with SV-10 was a major upgrade. GPS-3F is going to be a transformation. This mission also marked the 4th time SpaceX launched a GPS satellite that was originally assigned to United Launch Alliance under the National Security Space Launch Contract. That shift reflects the broader transformation happening across the U.S. national security space architecture, as SpaceX's Falcon 9 has proven itself mission after mission as a highly reliable vehicle for the country's most sensitive and strategically critical payloads. The Falcon 9 has now earned the trust of the U.S. Space Force, the intelligence community, and NASA through years of consistent, reliable performance, and that trust translates directly into contracts and launches that keep the country's space infrastructure modern and operational. With SV-10 now safely in orbit, currently being managed at Lockheed Martin's Denver Launch and Checkout Operations Center. Before formal acceptance into the GPS Operational Control Network, the United States GPS constellation sits at its strongest point in history. 32 active satellites in medium Earth orbit, 8 more in reserve backup status, and the most capable navigation signals ever broadcast from space, now covering every inch of the planet. The GPS-3 program is complete. The foundation has been laid, and the next chapter GPS 3F is already being built in Colorado, getting ready to push the boundaries even further. For 6 billion people around the world who open a map app every day without thinking twice about what makes it work, the engineers and soldiers and rocket builders behind this mission just quietly made the world a little more accurate, a little more resilient, and a little more connected than it was before. Word count. Cutoff, 490. There is something worth pausing on when you consider the scale of what GPS actually represents in the modern world, because most people genuinely underestimate how deeply embedded it is in literally everything. It is obvious in your phone's map app. It is obvious in aircraft navigation and ship routing and trucking logistics. But the less visible dependency on GPS is actually where the stakes are the highest. The global financial system depends on GPS timestamps to synchronize transactions between banks and exchanges. Power grids use GPS timing to coordinate the flow of electricity across massive networks. Telecommunications infrastructure relies on GPS timing signals to keep cellular networks functioning correctly. Emergency services dispatch using GPS continuously. Search and rescue operations from mountains to open ocean depend on it. Agriculture has been transformed by GPS-guided precision planting and harvesting systems that have increased yields and reduced waste at a global scale. The modern world is not just convenient because of GPS. In many critical ways, it would stop functioning without it. That is why the resilience improvements in the GPS-3 block matter so much beyond the military context. A GPS constellation that can be jammed or spoofed is a vulnerability not just for a soldier in the field, but for the entire global infrastructure that modern civilization rests on. Every improvement in anti-jamming capability, every hardening of the signal, every advance in orbital resilience is a direct reduction in the vulnerability of systems that billions of people and trillions of dollars of economic activity depend on every single day. When the U.S. Space Force talks about protecting GPS, they are not just talking about protecting military operations. They're talking about protecting the nervous system of the global economy. The story of how this final satellite got to the launch pad is also worth telling, because it did not follow the original plan. The GPS 3rd SV-10 mission was originally contracted to United Launch Alliance and their Vulcan Centaur rocket, a next-generation vehicle that has faced development delays. The U.S. Space Force made the decision to move the mission to SpaceX's Falcon 9, which has demonstrated the kind of reliability and launch cadence that national security missions require. This was the fourth time SpaceX inherited a GPS launch from ULA, and the fourth time it delivered. The decision to shift launches between providers based on operational readiness rather than political or contractual inertia reflects a maturing approach to national security space launch, one that prioritizes getting critical assets into orbit over preserving any single company's launch manifest. The booster that flew this mission, B-95, had previously been trusted with 6 batches of Starlink satellites. The fact that SpaceX is now comfortable flying the United States government's most sensitive and strategically critical navigation satellites on boosters that have also been used for commercial Starlink missions reflects just how reliable the Falcon 9 platform has become. Reliability at this level, the kind where a rocket that has flown 6 commercial missions is considered fully qualified for a national security payload of this importance, does not happen by accident. It is the product of thousands of engineers applying rigorous processes, learning from every flight, and building margins into every system so that the 7th flight is as dependable as the first. The completion of the GPS-3 block closes a chapter that has been years in the making and opens the door to the GPS-3F generation that will carry the constellation forward for decades. For everyone who worked on this program, the engineers at Lockheed Martin who built the satellites, the teams at the U.S. Space Force who managed and qualified them, the SpaceX crews who put them in orbit, April 21st, 2026 is a day that marks genuine mission accomplishment. And for the 6 billion people around the world who will navigate, communicate, work, and live just a little more reliably because this constellation is now at its strongest point in history, even if they never know it happened, the work was worth it.